All right. Good evening, ladies and gentlemen. Welcome back once again to the CERCA monthly expert talk. Actually, this talk by Dr. Sachin Ghude was scheduled in April, but had to be postponed to May due to some technical reasons. Our sincere apologies for the inconvenience. However, we are happy that this talk has now been scheduled, and we are proud to present Dr. Sachin, who is a senior scientist at the Indian Institute of Tropical Meteorology, Pune, who has pioneered an operational air quality early warning and decision support system for Delhi and NCR. The early warning decision support system has the capability to offer advisories to not just help zero in exact sources contributing to Delhi's air pollution, but also predict practical scenarios in winter for its mitigation. The decision support system was devised exclusively for Delhi and NCR and is an air quality early warning system to alert the citizens and the policymakers about the possible severe air quality events 10 days, 7 days in advance. Now, this system is based on the state of science online chemistry transport model, that is the weather research and forecasting with chemistry, which utilizes the anthropogenic emission inventory prepared by Energy Resources Institute for Delhi and the surrounding 19 districts. Dr. Sachin's area of specialization is in aerosol studies and taste gas measurement, and he has taken advanced research in numerical modeling of fog and air quality in India, inverse chemistry modeling and chemical data simulation, regional and global chemistry transport modeling for air quality and process level chemistry, remote sensing of tropospheric trace gases and satellite data simulation for emission inventory, air quality impact on health and ecosystem. Some of the exclusive research areas undertaken by Dr. Sachin. Dr. Sachin is also a recipient of the Boyce Cast Fellowship from the Department of Science and Technology, Government of India, and the Young Scientist Award from the International Union of Radio Sciences for Best Research Contribution. Dr. Sachin has done his MSc in Electronics from the University of Nagpur and PhD from the National Physical Laboratory, New Delhi, and University of Delhi. I would now like to welcome Dr. Sachin and invite him to deliver his talk. Over to Dr. Sachin.
Thank you, Dr. Himman. And actually, I'm really thankful for you to rescheduling this talk, and I'm really sorry I had to cancel my last talk due to some unavoidable circumstances, and I apologize for that. But I'm really thankful that you rescheduled the talk and given me an opportunity to talk on this particular subject. So I'll share my slides.
Sure.
So thank you again. And so I'm going to talk about operational air quality early warning and decision support system for Delhi NCR. What are the challenges and what are the successes in developing this air quality forecasting system? So this is the project we have done with NCAR USA, particularly the chemical data assimilation part. And Dr. Rajesh Kumar from NCAR was involved in this project as a PI. Apart from this, a lot of colleagues from IITM and IMD, specifically Dr. Gaurav Govardhan and Dr. Chinmay Jaina, who was extremely immensely contributed in the development of high resolution system and also the decision support system. Apart from this, Preeti, Praful, Shreyasi, Pooja, they are also contributing immensely as they are running this operational forecast day to day at our IITM supercomputing facility. So we know that the managing air quality in Delhi is extremely difficult because of we have a rapid expansion in transportation activity and industrial activity, and we have a lot of urban migration. And every winter season, we see this kind of news in newspapers and a lot of TV news and TV debates, particularly during from September to January months. Government of India is putting a lot of efforts to control or to manage the air quality in Delhi. But as of now, we don't see any immediate solution by which we can control the air quality levels in Delhi. So looking at this issue, it was thought that some kind of air quality forecasting system should be developed so that the citizens in Delhi NCR region and the policymakers or the enforcement agency should have some kind of information about the forthcoming air quality events in Delhi. And this was the motivation for us to design a very high resolution operational air quality forecasting system for Delhi. So the main aim of this system was to develop a system which can have a capability to capture the PM 2.5 levels, which contributes to the air quality about 200 AQI levels or about 300 AQI levels, particularly in poor, very poor, and severe air quality ranges, and not to miss any of the events which are falling in the category of very poor and severe air quality. So capturing these kind of events, very poor and severe, is extremely difficult for the current generation air quality models, because we are talking about the air quality levels or the PM 2.5 concentration, which is more than 500, 700, and sometimes it reaches up to the 1200 to 1500 microgram per minute.
Dr. Sachin, just a small interruption.
Yeah.
There's feedback that your voice is not audible to a few people, or the voice is, a little low.
Oh, okay.
Yeah.
Okay. So can you hear me now clearly?
Yes, I can hear you. I think.
Yeah.
Yes.
So
Yes.
yeah.
Okay.
Okay.
Yeah.
Yeah. So when we try to design this system, so it is extremely difficult to design a system where we want to capture a very high concentration of PM2 concentration that we see in Delhi in the range of like 700, 900 to 1500 microgram per meter cube. But we took this as a challenge and we developed a final year system which is capable of capturing such kind of extremely high air quality values in Delhi. So currently we are providing a forecast, short-term forecast from 3 days in advance, and a medium range forecast for 10 days. Yeah, so basically we started with scratch in 2020 with very little expertise in the air quality modeling and very limited resources. But we built up a system during Commonwealth Game 2020, and the system was in place to provide a air quality forecast and also the current air quality levels in Delhi. At the same time, we also realized that for checking or examining the accuracy of or the performance of air quality model, we should also have a reliable measurements available all across the city and all across the India. So we started building up the air quality monitoring networks in the metro cities by installing 8 to 10 air quality monitoring stations. And also we started expanding the network across pan India under the MAPAN project, and we develop a system which can give air quality forecast for Delhi region. Although the system was in place and operational, but the performance or the reliability of the forecast was extremely poor, and we consistently failed to provide a very good quality air quality forecast for Delhi NCR region, even though we had a advanced air quality model and the monitoring network available in Delhi. So this is the kind of forecast earlier we used to get. The red line shows the forecast by our SUPO model, and the blue line shows the air quality levels in Delhi. So here we can see that, and it was really very disappointing for us that we were not able to capture the extremely high PM 2.5 concentration in Delhi. All the extreme events like poor air quality events crossing 200 microgram per meter cube of values in Delhi was not captured well by the model, and model was completely underestimating the high air quality episodes in Delhi. So it was really a setback for us, and we started digging into the model. What are the reasons why we are not able to capture this kind of values in Delhi? And we tried to look into the different processes, different uncertainties in the model, and we started working on those processes and uncertainties one by one. So as we know that the air quality in Delhi basically is not only affected by the emission sources within Delhi, it is also affected by the emission sources within the NCR region. And our new analysis suggests that the contribution of emissions in Delhi is around 30 to 40%, and NCR equally contributes in the same magnitude. But at the same time, every winters we also get different kind of shocks, and that those shocks actually increases or reduces the air quality levels significantly. So one of those things are the non-local contribution to the air quality in Delhi, and which is coming from the stubble burning in the northwestern region of India, and also the dust from the extreme northwestern region of India. So it is not only the local sources are contributing to the air quality in Delhi, but at the same time, non-local sources also contribute significantly in the air quality in Delhi. And therefore, any air quality model which we use for the air quality forecasting should have this capability to account for these local and non-local source contribution. So one method is and one option is to improve this processes in the model itself, like improve the uncertainties or reduce the uncertainties in the anthropogenic emission inventories, biomass emission inventory, improve the processes that causes the natural emissions, and also the chemical processes in the model. And another way for improving the air quality is by improving the initial conditions of the air quality model, and that is where the chemical data assimilation comes into the picture. So then we build up a chemical data assimilation system using three-dimensional variational data assimilation scheme of the GSR into the WOFChem model. I'll not go into the details of this equation, but essentially what we are trying to do here is that we are trying to reduce the cost function J. So basically, we are trying to bring the model initial state as close as to the observations. So for building up this chemical data assimilation system, we have used Mozart gas phase chemistry, which is really very fast and designed for the operational purposes. And we have used Ghude aerosol scheme. Again, it is although it is not a very advanced aerosol scheme, but for operational purpose, this scheme is very fast. And then we relied on the Ghude aerosol scheme. The model is also forced with the chemical boundary conditions using Mozart for global chemistry transport model. Instead of giving real-time boundary conditions in our setup, we have used climatological boundary conditions to force the boundary with chemical fields from the global model. Again, the estimation of background error is very, very important, and if we really want to improve the accuracy of the assimilation. So usually what happens when you prepare a background error covariance for the data assimilation system, usually people consider the errors coming from the meteorological factors. But at the same time, the errors in the PM2.5 concentrations, which comes from the errors in the emission uncertainty, they also contribute immensely to and it is a source of uncertainty in the assimilation. So what we have done in our case, that we have considered both and included the errors from the meteorological initial conditions and also from the emissions. So for this, we have two different forecast valid at the same time, and this forecast we used to account for the meteorological error. To account for the uncertainty in anthropogenic and fire emissions, we developed a perturbation factor by considering different emission inventories, and this perturbation factor actually used to estimate the background error, which is contributed by the errors in the PM2.5 concentration. And here is the example of how the background error covariance looks like. This is an example for black carbon, and here you can see that the highest variance at the lower levels indicates large changes in aerosol mass concentration due to AOD assimilation will occur near the surface. So here you can see that so here you can see that the variance is very high near the surface. It means that when you do the assimilation, you will have more corrections near the surface, and then you have lesser corrections as you go up. And this figure shows how the assimilation improves the PM 2.5 forecast. So basically we are assimilating at 9 UTC, and you can see that after 9 UTC, black one is the observation, and then blue red one is the PM 2.5 concentration after the assimilation. And so this clearly tells that after doing the data assimilation, you get an improvement in the PM 2.5 concentration. Now, in case of background errors, if the background error is very large than the observational error, then the model aerosol concentration are adjusted to push the model AOD towards the Modi's AOD. And if background error is smaller than the observation, then model aerosol concentration is not J. And this is how we weight the model with the observational errors. So by doing this chemical data assimilation, we have two different setups. The first setup is the regional setup. So we do assimilation in the regional setup, which is at 10-kilometer resolution and which covers entire South Asian region. We use EDGAR emission inventory to cover the emissions all over India, but we replace EDGAR emission inventory with the TERI's 4-kilometer emission inventory to cover the NCR districts. There are 19 districts which comes under the TERI emission inventory. So we replace EDGAR emissions with the TERI emission inventories for those 19 districts. And for Delhi, we have our own emission inventory, which is a 400-meter resolution. So for Delhi, we have used our own 400-meter emission inventory. This regional setup is driven by the assimilated meteorology from the ensemble Kalman filtering at 12.5 kilometer grid resolution from the IITM IMD GFS forecast at T1534 resolution. So once we drive the model with this assimilated meteorology, then we assimilate the fire emissions using Modi's 1 kilometer and VIRS fire at 370-meter resolution. So we first assimilate the fire information into the model. So once we do that, then we assimilate the aerosol optical depth from Modi's, both using Aqua and Terra, and the Modi's aerosol optical depth we assimilate at 10-kilometer resolutions. So once we do the fire emission assimilation and then Modi's data assimilation, then we provide surface PM 2.5 concentration from all over air quality monitoring stations located across India. So we do then surface data assimilation. So this is the regional setup, assimilation setup, which provides the air quality forecast for 3 days in advance and 10 days in advance at 10-kilometer resolution for entire Indian domain. So once we do the assimilation, it takes around 5 to 6 hours. We start our assimilation setup somewhere around 11:30 in the morning, and we do the all processing, and it gets over by evening 5:30. So once we have the regional assimilation setup ready, then we go for the city specific setup. So for city specific setup, we actually dynamically downscale the 10-kilometer forecast from regional setup to the 2-kilometer resolution forecast covering all entire North Indian region. So this is an intermediate setup, and from 2-kilometer high resolution setup, we again downscale it to the 400-meter resolution setup, which is focused on Delhi region. So in addition to the data assimilation in a regional setup, we also assimilate. We provide the high resolution emission inputs to the city specific setup at 400-meter resolution, and we also assimilate the air quality observations from Delhi NCR region, which has a 43 monitoring station. So data from this 43 monitoring station goes into the assimilation at very fine resolution. So we assimilate twice in a day. One is at 9 UTC and another one is at 16 UTC. So apart from this, we have also used latest land use land cover, high resolution land use land cover map from the Sentinel-2 data set. We have done this because we wanted to capture the heterogeneity in the surface temperature, boundary layer height, and the moisture field in the model. So instead of relying on the Modi's land use land cover pattern, we have actually replaced the Modi's land use land cover pattern with the high resolution Sentinel-2 land use land cover data set. So once we do all these activities, it takes around another 6 to 7 hours to run the forecast, and by midnight, around 2 p.m., our entire forecast is ready. And here you can see that how the assimilation works. So how much improvement does the different assimilation steps actually contribute to the improvement or improvement in the accuracy of the forecast. For example, this is a snapshot of assimilation of Modi's Terra AOD on 6 November at 6 UTC. So left hand side figure shows the Modi's aerosol optical depth on that particular day. So you can see that not many region of India is covered by the Modi. There are certain gaps in the data. So assimilation is only occurring over the places where the data is available, satellite data is available. The Modi's aerosol optical depth, if you compare with the model aerosol optical depth without data assimilation, you can see that there is a significant bias between the model aerosol optical depth and the observed optical depth. But after doing the data assimilation, you can see that there is a lot of improvement in the modeled aerosol optical depth, and you can see that now the observed simulated simulated aerosol optical depth with assimilation closely matches with what see in the observation. So this is how the satellite data assimilation improves actually the PM 2.5 forecast. This is again an example how much improvement we see when we do the satellite data assimilation. So here black one is the observed, blue one is the observed PM 2.5 concentration in Delhi region. Black one is the forecasted PM 2.5 concentration but without assimilation, and red one is the PM 2.5 concentration forecasted by the model with data assimilation. And here you can clearly see that once we do the satellite data assimilation, you get a improvement in the PM 2.5 forecast during the days when you have a very high amount of PM 2.5 concentration in the atmosphere. However, even after doing the AOD data assimilation, you can see that model is still under predicting the observed PM 2.5 concentration in Delhi. Although the model levels have increased from about 100 microgram per meter cube up to the 350 microgram per meter cube. But by doing a model Modi's data assimilation, still model is not able to capture the extremely high PM 2.5 concentration up to 700 and 600 microgram per meter cube that we see during the peak events. Even also in Delhi, when you can see that model is, although the model is improved after doing the data assimilation, but still it is significantly under predicting the observed PM 2.5 concentration. And this is the period when you have a lot of activity going on, biomass burning activity going on in the northwestern states of India. So then we realize that we need to have a real-time fire emission inventory in the forecasting model, so that we can later on pick up the underestimated PM 2.5 concentration in the model. So we then adopted the fire emission inventory from NCAR, which is based on from the various data set. Like it gives the emission outputs by considering the fire count, then burnt area product, and vegetation burn, then land use land cover classification, vegetation continuous fields, and fuel loading emission factor. So by combining all those information, fin emission inventory gives you the daily fire emissions from the stubble burning. However, unfortunately, this emission inventory is not available in real time for us because it takes almost 24 hours to update the information. So the emission inventory is not available in real time. And another disadvantage of this emission inventory is that it doesn't provide you the forecast of fire. So how much fire will occur next day or next 72 hours. So this kind of information is difficult to get because you cannot predict the fires, and it is not available in the fin emission inventory. And this is one of the shortcoming of the emission inventory, fire emission inventory. So we came up with the solution, and we tried to develop some kind of algorithm by which we can predict the near real-time fire information, and at the same time we can generate some type of air quality fire forecast. So what we did, we prepared the daily fire emission history for each model grid resolution based on NCAR fire emission inventory. So then we take a real-time fire account data from the Modi's and VIRS fire location, and we use to find where the fires are actually burning in the model grid. So we then track the similar cases of the fire activity in the past for the same grid. And once these fire activity is identified based on the past cases, then the same emissions in past is provided to the identified grid as a fire emission for the real-time forecast. We have also prepared a daily fire climatology, which we use as a predictor for next 2 days. So what we have seen that after providing the near real-time fire emission inventory, after doing the Moody's data assimilation, so we get a lot of improvement in the air quality forecast. So here you can see that when we included the fire emissions, we see a largest increase in the surface PM 2.5 due to both Moody's data assimilation as well as from the fire emission. And we compared this with the observed data from the stations located in Delhi and also in the northwestern region of India. And here you can see that blue one is the model forecast without fire emission, black one is the observation, and red one is the forecast with the data assimilation, means with both Moody's aerosol optical data assimilation as well as the near real-time fire emission assimilation. So you can see that after inclusion of the fire, you get a tremendous improvement in the air quality forecast, and you can see that the model is now able to capture the high peaks that observed during the fire events. So this is the next step which actually improved our forecasting capability. Now again, so considering the climatological fields for the forecast is not good, because we realize that if we go for the climatological fields for the forecast of fire, you don't get the variability. So this is an example for 2nd October, 3rd October, and 4th October climatological fire fields, and you can see that there is a hardly variability between these 3 days. And the true fire counts are given in the middle panel. So this is on 2nd October, top panel, middle panel is on 3rd October, and bottom panel is 4 October. So one of my colleague in IITM, Dr. Bipil Kumar, he has developed some kind of AIML technique by which we can actually recognize the pattern in fire emissions, and then that pattern recognition can be used to predict the fire. And once we do this AIML based kind of pattern recognition, we have seen that this AIML model has some skill to predict the fire emission for next 2 days. And here you can see that the last panel, right side panel, actually captures the variability between the days. And this is not yet implemented in the forecasting system, but we are planning to implement this thing in the coming winter season. So once we do the fire data assimilation, then also we have realized that model is not able to capture the extremely high concentration in Delhi. So what we did, we have again started assimilating the PM 2.5 concentration in the fine resolution setup. So we are almost assimilating stations from data from the 43 air quality monitoring station. And here again, you can see that black one is the observations, red one is observations without assimilation, and blue one is the with data assimilation from all these 43 air quality stations. And you can again see that once you do the surface data assimilation, you get a tremendous improvement in the PM 2.5 forecast over Delhi. So earlier the model was driven with the Moody's land use land cover category, and you can see that this top panel shows the Moody's land use LULC map, and you can see that all over Delhi it is a urban place, and therefore the temperature heterogeneity is not there in the Moody's. Just a moment, let me. So here you can see that the temperature heterogeneity is not there in the Moody's LULC, even the moisture availability, and you can see that the PBL height is uniform all over Delhi. But when we replace the Moody's land use land cover with Sentinel-2 land use land cover with very high resolution 10 meter or 20 meter of data, we actually started getting the temperature heterogeneity in the Delhi, and also the heterogeneity in the water vapor field. And you can see that now the boundary layer height is much lower than what we see in the Moody's LULC. So this has also impacted the PM 2.5 forecast, and you can see that after replacing the Moody's LULC with the Sentinel LULC, you can see that there is an improvement of about 100 microgram per meter cube PM 2.5 concentration in Delhi. So finally, combining all these different steps in one model forecast, we have seen that there is a tremendous improvement in the PM 2.5 initial conditions, both due to the satellite data assimilation, then surface data assimilation, fire data assimilation, and change in the LULC category. So this particular figure shows the impact of improvement in the initial condition of the model after doing all the data assimilation at assimilation cycle t is equal to 0. So here red one is again the without assimilation initial condition, blue one are the observation, and green one is the after assimilation. And you can see that now the model is able to capture extremely high concentration of PM 2.5 in Delhi, and during the heavily pollution event, like from 27th October to 11th November, we have extremely high concentration of PM 2.5, and the initial condition was able to capture those particularly high concentration of PM 2.5. This is during the biomass burning period and during a peak winter period when there is a no biomass burning, but most of the PM 2.5 concentration is driven by the stable meteorological conditions. During that conditions also, the improvement in initial condition was tremendous. So then we evaluated the quality of our air quality forecast at 400 meter resolution, and we tried to see whether this entire assimilation method actually translated into the improvement in the air quality in Delhi. And here you can see that blue one is again the observations, and red one is the forecast coming from the 43 stations all over Delhi. And you can see that now model has a pretty good skill in capturing the high values of the PM 2.5, low values of the PM 2.5 concentration. You can see that there is a sudden change. If you look at 6 November and 10 November, there is a sharp rise in PM 2.5 concentration, and model is able to capture those sharp rise. Model is also able to capture the slow varying increase in the PM 2.5 concentration in Delhi. So overall, the model has a very good skill now to capture not only day-to-day values, but also the hourly values of PM 2.5 concentration in Delhi. And the overall bias that we see in the model is around 13%. So this evaluation was performed for winter season of 2019 and 2020 season, and we wanted to see whether the forecast is consistent. Then we also compared during winter of 2021 and 2022, and you can see that the performance of the model was extremely good for winter season of 2020 and 2021. So this season also model was able to capture all the peaks and the variation in the PM 2.5 concentration in Delhi. Specifically, the model was able to capture the extreme high values of PM 2.5 up to 900 microgram per meter cube whenever the air quality goes into the extremely severe range of AQI. Again, the consistency of forecast was proven in the latest winter season, that is 2021 and 2022. Even in last season also, model gave a very good air quality forecast for entire winter season. So earlier we were talking about the values that we see in Delhi, which is very high, extremely high concentration, and the performance is very good. So we also wanted to see whether the performance of model is reliable for other cities of India where the assimilation is going. So we check the performance of the system for Bangalore, where almost 10 data from the 10 air quality monitoring station is going into the assimilation at 10 kilometer resolution. And here also you can see that the performance of system is extremely satisfactory, even at the very low concentration of PM 2.5 from 20 microgram per meter cube up to the 70 microgram per meter cube. And even in Bangalore also, model is able to capture all the day-to-day variability and hourly variability that we see in Bangalore. So overall, assimilation of data from various platforms has tremendously improved the skill of our forecast and accuracy of our forecast, and we can now reliably see that this forecast is useful for the air quality management in the various part of India. So we also saw the capability of forecasting system is good to predict the dust event. So this is one of the event that occurred recently in January 22 and 23, and we had a severe dust storm in Oman and southern Pakistan. And this photo is taken from my balcony, so the visibility was not more than 2 kilometers. And then I looked into the forecast, and here you can see that the storm started somewhere around 22 January, 20 January, in the Oman and southern Pakistan, and that the storm hit the Pune, Mumbai, and Ahmedabad somewhere around 23 January. And you can see that the model is able to capture not only the peak of PM10 concentration due to the dust storm hitting of the dust storm, but it also captures the phase of the dust storm. So overall, model is not only capturing the anthropogenic emission related enhancement in the air quality, but it also is extremely successfully capturing the air deterioration in air quality that is occurring due to the natural events like the storm. So we also did some statistic to statistically evaluate the quality of our forecast, particularly for the category where the air quality is more than 300 and more than 400 AQI. And this was one of the aim, whether the system should capture the extremely high air quality events in Delhi. And you can see that the model, if you look at the first day, second day, and third day of forecast, the normalized mean bias is within 5%. So even on the fifth day of forecast, model is not deteriorating beyond 5%. And if you look at the normalized mean fractional error, it is less than 20% for the severe air quality. Usually we consider if the normalized mean bias is less than 50% and normalized mean fractional error is less than 25%, then the quality of forecast is considered to be extremely good. And so based on this statistical parameter, you can see that the performance of this forecast is extremely good. If you look at the false alarm rate for various categories of air quality index and the accuracy of forecast for unhealthy, very unhealthy, and severe air quality, you can see that accuracy of this forecast is more than 80% for all these three categories, and false alarm, whether the severe air quality event will occur or not, is less than 25%. This is the kind of forecast accuracy we have been getting consistently for last 3 seasons. So looking at the success of our air quality forecasting system, then the Commission for Air Quality Management in Delhi and NCR region, they approached us and they wanted us to develop a decision support system. So they said, you are able to forecast the air quality in Delhi, but can you provide us the information about which sources are contributing to the air quality in Delhi and what are their magnitudes? So we, as per the direction of the CAQM, Commission for Air Quality Management, we started developing the decision support system for Delhi NCR region. So what we have done essentially here is that we used our existing air quality forecasting model and we extended its capability to provide a decision support kind of information from the forecast. So for that, what we have done, we have implemented around 400 passive tracers in the model. Those are the tag tracers in the model, and which gives information about around 2000 variables. So we implemented these tracers in the existing air quality forecasting model. These tracers are basically implemented to track the emissions from various sectors and various sources and various districts from Delhi, within Delhi and surrounding Delhi region. We have also implemented these tracers for identifying the contribution of fire to the air quality in Delhi. And these tracers are also implemented to give the scenarios. Like what if we implement the odd even category, then how much improvement we can see in Delhi's air quality? Or if we reduce the traffic emission by 20% or industrial emission by 40%, if we go for such kind of combinations, so how much air quality improvement we can see? That kind of information is now coming from our air quality forecasting system. So now early warning and possible ways to prevent the occurrences of the event, this kind of information is actually coming from this system. So for this, what we have done, we have taken the TERI's emission inventory, which is available at 4 kilometer resolution for Delhi and surrounding 19 districts. And we tracked the different emission sectors and different emission districts belonging to these 19 districts. So once we simulate the tracers along with the air quality forecast, then it gives you information about the source contribution of local sources and non-local sources. So we get generally this type of maps, spatial maps, hourly spatial maps, which tells you about the contribution of different districts to the air quality in Delhi. For example, this particular map at 11 UTC on 9 November 2021 tells us that Delhi's contribution to the Delhi's air quality is somewhere around 35%, and then 10 to 15% contribution is coming from the Sonipat and Jhajjar and Rohtak, and remaining districts are contributing less than 5% to the air quality in Delhi on that particular day and on that particular hour. At the same time, you also get how much contribution is coming from the other region, excluding these 19 districts. So it was around 9%. And how much biomass burning contributing? So that time on that day, the biomass burning contribution was around 42%. So this kind of source apportionment is numerical source apportionment also coming from the air quality forecast. So for example, this is the 5 days forecast for source apportionment of PM 2.5. And here you can see the contribution of different sectors within Delhi and different districts in Delhi. For example, this yellow color shows the contribution of Delhi's transportation sector to the air quality in Delhi, and you can see that its contribution varies between 10% to 20% depending upon the ventilation index and boundary layer height. Such type of information is coming with the forecast. You also can develop a scenarios, and this is one of the example of scenarios. If you reduce the emissions from all over 19 districts in Delhi and surrounding districts by 60%, then how much improvement you will expect in the air quality for next 5 days. So here you can see that if you reduce the air emissions from all the sectors in these 19 districts, then you can get if you reduce the emissions by 60%, you get the improvement in air quality by about 45%. So these kind of scenarios are also available with the forecast. And the best part of this DSS system was that it is not that we are running it standalone and giving it the forecast to the public, but this system was extensively used by the CAQM in this season. For example, we predicted that on 11 November, the air quality will touch the severe plus category, and similar air quality events will also occur on 19th November. So based on our forecast, what has happened, the Delhi government started restricting the activities in Delhi NCR region by imposing temporary restrictions on the transportation activity, construction activity, and then they have stopped the bricklaying activity. And also CAQM also, they have directed some precautionary measure, and the effect of that is that we could able to restrict the severe event, not going air quality in the severe event, but we could restrict the air quality below 400 AQI. So the best part of it is that the system has completed the loop. We have forecasted the air quality events. The enforcement agency, the policymaker took the note of that system. They acted promptly, and eventually we could able to reduce the air quality in Delhi by 22 to 23% during this severe kind of air quality event. So I would say that this is one of the first and high resolution operational air quality forecasting system in the globe. And it was much appreciated by the national and international agency, also by the CPCB and CAQM, and now it is extensively used by the policymakers in India. So all this information we provide in the website called AQEWS and DSS, and anyone can access this forecast, access this website. If somebody wants to see what is the air quality, current air quality in Delhi, and how much is the air quality that we expect for next 3 days, how is the spatial pattern of air quality, that kind of information is available on air quality early warning page. And if somebody wants to go into detail analysis, so it is also available in the analysis page, where you get day-to-day verification of the forecast, contribution from the different sources. All this information is available in the air quality website. And for the DSS website, we have developed a new website for decision support system. And here you can see how much, what are the sources those are contributing to the current air quality levels in Delhi. And if you also play with the different scenarios on this website, and you can generate your own scenarios, and you can identify how much air quality improvements you expect when you apply those scenarios for air quality management. Yeah, so this is all I want to say. Thank you. And I would like to specially acknowledge the efforts by our former secretary M Rajivan, whose visionary initiatives have actually behind this implementation of early warning system. And then our director, former director, Professor Ravi Nanjundaya, Dr. R Krishnan, DG IMD Dr. Mohapatra, and former DG Dr. Ramesh. They have supported a lot to implement this system, and finally we could achieve a very high quality air quality forecasting system for Delhi NCR region. Thank you.
Thank you very much, Dr. Sachin, for an excellent talk and a wonderful presentation. We have a lot of questions lined up for you, and I would now request Keetika, our project scientist, to moderate the question and answer session. Over to Keetika.
Yeah, thank you so much, sir, for this talk. On the behalf of CERCA, once again, I would like to thank you for such a meaningful and interesting work. Also, I would like to thank the audience for being the patient listeners. Now we'll be moving to this QA session. We have some questions posted in the chat box from our participants, but due to some time constraint, we won't be able to take all the questions, but we'll be taking a couple of them. So the first question we have from Aman, do you have any plans to release the high resolution emission inventories over Delhi, Pune, Ahmedabad, developed by IITM under SAFAR project to the general researchers in India?
Yeah, actually, it is available for the general researcher, and one can just email to the group leader who has developed this emission inventory. So Dr. B.S. Murthy is the in charge of this emission inventory, and one can write to him and get the emission inventory. So it is all open because it is developed by the MOS efforts. So it is all open.
Okay, sir. So which modeling software?
And also we have a partner project with CDAC, Urban NSM project. So we are developing a methodology by which all these forecasts, all these data set, emission inventories will be available to the end user just on one click. So this kind of system we are developing, and hopefully this system will be available by next year.
Okay, sir. So the next question is, which modeling software do you use in this analysis?
Which?
Modeling software.
So modeling software, basically we have used this WRF-Chem, weather research forecasting model coupled with chemistry for air quality modeling, and we have used grid point statistical interpolation model for data assimilation with three-dimensional variational data assimilation scheme.
Okay, sir. So the land cover classification for Sentinel-2 is readily available, or this was also carried out in-house?
No, it was carried out in-house. Basically, it was carried out by our partners in CDAC. So they have prepared these maps, and then once we prepared those maps, then we replaced Modi's land use land cover with the Sentinel-2 land use land cover. Yeah. So it is not available. Data is available, but one has to prepare those maps, because what we have done here is that we have reclassified the urban map, and we have reclassified it into medium intensity urban maps, high intensity and low intensity reclassification we have done. And that is why we are able to capture the heterogeneity in surface temperature and moisture.
Okay, sir. Sir, regarding the forecasting, we have a couple of questions. Do you reduce the SAFAR inventory emissions for Delhi by 40% for the forecasting?
Yeah. So what? Basically, earlier we used Edgar emission inventory, but it was completely under predicting. Then we used emission inventory developed by MOES under SUFFER program, and then we did some sensitivity experiment, and we realized that the SUFFER emission inventory has some higher estimation, and then we reduced the transportation sector emission by somewhere around 20%, and residential emissions by 20%. So collectively, we reduced emission by 40% to capture the levels PM2.5 levels in Delhi.
Okay, sir. So this evaluation was done at a forecast of 48 hours or 72 hours?
So we have done evaluation for 72 hours. Also, as I said, we are also developing generating forecast for medium range 10 days. So evaluation is also done for 10 days, but because of time constraint, I did not include those sites for 10 days forecast.
Oh, okay, sir. So next we have this, can DSS be designed to give sectoral contribution from the NCR districts and not just district-wide contribution?
Yeah, so sectoral contribution is available in DSS, but it is restricted to only Delhi. So what we are currently doing, we are taking 8 major sectors in Delhi that has more contribution to the Delhi's air quality. So those 8 sectors we are currently tracking, but remaining 19 districts, we are just tracking the 19 districts. Because this is a massive task. You need to implement traces for each and every sector and subsector. So it takes time, and computationally also it is extremely expensive. So we are now we are trying to reduce this complexity in the computation by implementing more and more traces, but it will take some time. So this year we'll track sectors in 19 districts surrounding Delhi also.
Okay, sir. So what is the confidence level of 5 days prediction, as burning activity is very erratic? Like in Punjab, burning is increased on holidays as government staff is on leave. So what would be your comment on it?
So at third day, if you look at the air quality forecast through on third day, so the confidence level basically, if you look at the accuracy, it is still 80%, 82%.
Okay.
Yeah.
Sir, how is the waste combustion is incorporated into this model?
Which combustion?
So waste combustion.
No, we are not accounting for waste combustion. It is actually coming from the emission inventory.
Okay,
Yeah.
okay, sir. Sir, the last question we have, do this early warning system have applicability all over the globe? Does that mean
Yes.
we can use it anywhere on the globe?
So we can use similar setup and for anywhere in a globe. Yeah. So currently
Okay.
we have set up for India and for Delhi, but now we'll be setting it up for Bhubaneswar, Pune, Bangalore, Ahmedabad. But certainly this is a setup. This is a mechanism that we have developed, and we can replicate this complete setup for any other cities over the globe.
Okay, sir. Sir, next one more. How farm fires are assimilated in the model considering satellite pass only twice in a day?
Yeah, so this is still a source of uncertainty when we assimilate the fire emission, but when you go for real-time forecasting, so you need to rely on the information which is readily available that time. So as far as I know, this is only the information in real time which is coming about the fire information, and we are trying to assimilate that information. There are uncertainties because satellite misses a lot of fires which occurs in the morning or late night hours, but this is getting compensated by the assumptions in the fire emission inventory, because what fire emission inventory does basically is that they do not consider how much crop residue is actually burnt in the fire. They assume that whenever they detect the fire, they assume that entire crop is burnt, but this is not a ground reality. Farmers don't burn the entire crop, but this assumption actually little bit compensating the unmissed fire in the fire emission inventory. This is a source of error, but it is getting compensated. Two errors are getting compensated because of certain assumptions in the fire emission inventory.
Okay, sir. So thank you so much for all the answers.
Thank you.
So over to you, Hemant.
Thank you, Dr. Sachin, for an excellent talk. And we all were enlightened by your talk and the presentation. And I'm very sure that everybody must have, enjoyed your presentation and will definitely take home a lot of learnings from your presentation. I also want to thank the participants who waited for your talk in the month of April, but then again rejoined your talk in the month of May. Thank you all once again, and thank you, Dr. Sachin, for this talk. Thank you very much, everyone.